You ever wonder how a self-driving car actually sees the road? Or how your phone can just, build a 3D map of a room? It's not really about taking better pictures. It's about understanding what's in them. Today, we're going to dive into how computers take a bunch of flat 2D images and somehow build a rich 3D model of reality. And get this, the secret ingredient that makes it all work isn't some fancy new camera lens or a giant sensor. Nope, it's something way more fundamental. It's math. Pure, elegant, and, as we're about to see, insanely fast math. Okay, so take a look at this. It might look like some kind of abstract, grainy photo, but it's not a photo at all. What you're looking at is a 3D point cloud. It's a super precise geometrical model of a building that was built entirely from a handful of normal pictures. Every single dot you see there, that's a point in real three-dimensional space. And that is the billion-dollar question, isn't it? How does a machine look at a bunch of flat photos and figure out the depth, the shape, the whole structure of the world? I mean, that jump from 2 dimensions to 3, it really does feel kind of like magic. But it's not magic. It's the sheer power of calculation. See, to build that 3D model, a computer has to chew through a storm of complex equations. We're talking polynomial equations. Yeah, the same kind you might remember from algebra, but way, way more complicated. And it has to solve them thousands of times every single second. And that brings us to our next big point here, the need for speed. Because in the world of computer vision, being fast isn't just a nice little feature, it's literally the entire game. At the very heart of all this are these things called minimal problems. Think of them like the individual Lego bricks of understanding geometry. Each one is this tiny but absolutely crucial math puzzle. And when a computer solves one, it reveals one small truth about the 3D world, using just the clues from a 2D image. So here's where it gets really crazy. Things like self-driving cars, they can't just solve one of these little puzzles. They're dealing with a constant flood of messy, imperfect data from the real world. So they use this framework called Ransack to sift through all that noise. And Ransack works by just hammering these minimal problems over and over, thousands of times a second, to find the answer that shows up most often. That's how it finds the most reliable view of the world. It's an absolutely immense amount of work for a computer. So for years, how did scientists even begin to handle this incredible need for speed? Well, they pretty much relied on one single, powerful, state-of-the-art method. It's called the Grosvenor basis method. And for a long, long time, this was the gold standard. It works by creating what's basically a mathematical recipe. They call it an elimination template that tells the computer the exact steps to solve the problem. It's super optimized, a real workhorse at the field. The only little catch? It doesn't always cook up the absolute smallest or fastest recipe possible. And in a world where every single nanosecond counts, that little not always is a huge opportunity for improvement. This has totally opened the door for new contenders, smarter, leaner, and just more efficient ways to solve these mission-critical puzzles. And this is where the latest research just comes in and completely changes the game, with some incredibly clever new ways of thinking about the problem. Okay, so the first one is the sparse resultant method. And the idea here is just beautiful in its simplicity. Researchers found that if you take your original really tough problem and you just add one more special, simple equation to the mix, it completely changes the structure of the problem. It morphs it into something called a standard eigenvalue problem, which is just a fancy way of saying it turns into a math puzzle that computers are incredibly good and fast at solving. It's like finding a universal adapter for a plug that just would not fit before. It's so clever. The second new approach is a bit different. It's a powerful automatic generator. So instead of relying on one fixed method, this thing is more systematic. It can handle a wider variety of equations, and it basically just tests a whole bunch of different combinations to find the absolute smallest, most efficient recipe for whatever problem you throw at it. It's less about one clever trick and more about a super smart search for the perfect solution. And does it work? Oh yeah, absolutely. This table just lays it all out perfectly. These solver sizes, that's pretty much the complexity of the recipe, right? A smaller matrix means fewer calculations, and that directly translates to a faster solution. Look at this. For one key problem, the recipe size was cut by nearly half. For another one, it was more than halved. These aren't just tiny tweaks. These are massive, massive leaps in efficiency. So what does solving all these equations actually do? Well, check this out. Correcting for camera lens distortion is a perfect example. The image on the left, that's what the camera actually sees with that weird warped fisheye effect. But by solving the minimal problems for that distortion, the computer can create the clean, corrected image on the right. That's the math, right there, in action. So we know these new methods create smaller, more elegant solutions. But what does that actually mean when the rubber hits the road? Let's talk about the real-world performance payoff, because this is where it gets exciting. For something like hybrid navigation in a self-driving car, where you're mixing data from a simple camera with a more complex system, the new solver is 20 to 30 times faster. That's not just an improvement, that's a mind-blowing leap forward for a system that has to make life or death decisions in a split second. And hey, this isn't just about what we can see. The exact same mathematical ideas apply to sound. For a smart room that needs to figure out where all its speakers and microphones are on its own, these new solvers are up to 1.8 times faster than what they had before. You know, the researchers behind all this really put it best. They said their experiments show that their solvers are both more accurate and faster than the existing alternatives. I mean, what more could you ask for? It's not a trade-off. It's just better all around. So, what's the big takeaway here? The bottom line is that this whole field is basically a race to find the fastest, smallest, most elegant solver. There isn't one silver bullet, no single best method that works for every problem. But what this new research gives us is a powerful new toolkit. Now, researchers have more options to pick from, letting them craft the absolute perfect recipe for any challenge. And that's what's pushing the boundaries of what machines can see and ultimately understand. Which kind of leaves us with this one huge, fascinating question to think about. The math that lets machines see our world is getting faster and more powerful at an exponential rate. So as they get better and better at understanding the geometry of everything around us, from bustling city streets all the way down to the molecules in a cell, what profound problem do you think they'll help us solve next?